All right, this is part 2 of our applications of linear equations. Most of the problems that we'll see right here are what are called rate time distance problems. If you recall, rate times time equals distance. Or if you solve that for time, you get, we've done this in the past, time is distance divided by rate. Or if you solve for r, you would get distance, or r equals distance over time. Those are all different versions of the same formula. Let's look at our first example here. Two cars leave the same place at the same time, going in opposite directions. One car travels 40 miles per hour, the other 50. How many hours will they be 300 miles apart? Okay, so they leave the same point. One car is going this way. The other car is going that way, different speeds. They do leave at the same time. So both cars start and then they both stop at the same time once this entire distance here is the 300 miles. So the key to this is to realize that the entire total distance is 300 miles. All the rate time distance problems that we have here can be solved using a table with 6 boxes like this. Here, in there you put the rate, and here's the time, and this is the distance. Rate times time equals distance. On the side here, we'll put the, we'll call it the first car, and then this is the second car. Now, how fast is the first car going? It's going at a rate of 40 miles per hour, so it's going to be a 40 in there. The second car is traveling at 50 miles per hour, so I put a 50 there. Now, what we're trying to find is how many hours will they be 300 miles apart? We want to know the time, and so that's my variable, t. And this one is also traveling for the same amount of time, so I can use t there as well. Once again, remember that these cars start and then they stop at the same time, and so their times are equal. I can put t for each one. Since rate times time equals distance, rate times time equals distance there, I multiply across 40 times t. That gives me the distance that the first car traveled. If I put that up here, this distance right here then in red is 40t. 50 times t is the distance that the second car travels. This is 50t. Now for our equation, I'll put it on the side here. The total distance is supposed to equal 300. Well, the total distance is the 40t, the distance that the first car traveled, plus 50t, the distance that the second car has traveled. That should add up to 300. That's the equation I need to solve. 40t plus 50t is 90t. Divide both sides by 90. And I get t equals, I can reduce that, that's 10 over 3, which is 3 1/3. 3 1/3. Okay, that's our answer. So I'm going to write that out like this. The cars travel for 3 1/3 hours. 3 1/3 hours. If I want to check the answer, what I need to do here is just plug it in. Right up here. Let's see, I'll put it up here. Here's my check. Squeeze it in here. Let's see, I'll put it in green here. Time is 10/3 for each one. So 40, I'm going to multiply across here. 40 times 10/3 plus 50 times 10/3. If this is the correct answer, that should add up to 300 miles. That's 400 over 3 plus 500 over 3. That's 900 over 3, and that is 300, and so it does check out. Check. Okay. Next question. Two cars leave the same place. One car leaves at 8 a.m. and travels at 35 miles per hour. The other car leaves at 8:15 at 40 miles per hour in the opposite direction. How many hours will they be 140 miles apart? Very, very similar to the last problem we just did. The only difference is that one car leaves before the other, and so it adds just a little bit more difficulty to the problem. So we have one car going this way. We have one car waiting for, what is it, 8 to 8:15. So it waits 15 minutes, and then it goes, and let's say it gets that far, and we want to know how far, or how much time will they be 140 miles apart. All right, let's make our table here. Rate times time equals distance. So our first car, second car. The speed of the first car is 35 miles per hour, and we're looking for the time that it is that has been traveling, which so we'll use t for that. And so its distance, just like in the last problem, its distance is rate times time, so that's 35 times t. Now the second car travels at 40 miles per hour, and its time is not the same. It's not a t because it left 15 minutes after the first car, and so its time would be 15 minutes less. 15 minutes less than the first car. Actually, let me fix that. I can't use minutes here. I got to write in, we're in mile per hour, so 15 minutes is a fourth of an hour. Put it here, 15 minutes. It's 1/4 of an hour. Multiply across 40 times t minus a fourth, just like that. Now the total distance is supposed to equal 140, and so just like the last problem we did, 35t plus the 40t minus 1/4 should add up to 140. That's the equation I want to solve. Okay, so let's solve it. 35t plus, we got to distribute that, 40t minus 40 times the fourth is 10. Add 10 to both sides and combine your like terms. We got 75t equals 150. And dividing both sides by 75, and we'll get 2 hours. So if I go back up here, t is 2. This is 2. And this is 2 here, so this is 2 minus a fourth. That's going to be 1 3/4 hours. 1 3/4 hours. I'll write it down here for you. So our answer is right here. The first car travels 2 hours. The second car travels for 1 3/4 hours. So remember that it left 15 minutes later, so it was traveling for 15 minutes less time, as we specified right there. Okay, next one. Jeff can bike to work in 3/4 of an hour. By bus, the trip takes 1/4 of an hour. The bus travels 20 miles per hour faster than Jeff rides his bike. How far is it to his workplace? Okay, here's our table. Rate, time, distance. And the two things we're doing here is we're going by bike and by bus. Okay, we know the time here. We know that the time it takes him to bike is 3/4 of an hour, and we know it takes the bus 1/4 of an hour to get to work. Now the bike travels, it says 20 miles per hour faster than Jeff I said again, the bus travels 20 miles per hour faster than Jeff rides his bike. So if we let x up here equal the speed biking, that's an x. The bus goes 20 miles per hour faster, so the bus's speed is x plus 20. Now I'm going to find the distance. Remember that rate times time does equal distance, and so I'm just going to multiply across 3/4 x. This will be 1/4 x plus 20. Now in the last problem we added the distances, but that's not what we have here, because if Jeff rides his bike to work or whether he takes the bus to work, the distances are equal. We don't add them together here. They're equal. We set them equal to each other. So I want to set this equal to that, because both of those represent the distance to work. And so the equation I want to solve is 3/4 x equals 1/4 x plus 20. That's the equation we're going to solve. Let's, you know what, let's multiply both sides by 4 to get rid of the fractions. Times 4 there. That'll give us 3x equals x plus 20. Subtract x from both sides. 2x equals 20, and so x will be 10. X is 10. Now, that's not actually what the problem asked for. The problem asked how far is it to his workplace, so I'm not quite done yet. I need to go back up here. This is 10, and this is a 10. That means that he bikes at the rate of 10 miles per hour. The bus then goes 30 miles per hour, 10 plus 20. I could use either one of these to get the distance to work. I'll use the top one, it's easier. The distance is 3/4 x, but the x is 10, so 3/4 times 10 is 30/4. And if we simplify that, we get 7.5. 7.5. And so the answer is the distance to work is 7.5 miles. There's our problem. Okay, here's another. Mary begins jogging at 5 a.m., averaging 3 miles per hour. Joe leaves at 5:30 a.m., trying to catch up to her, averaging 5 miles per hour. How long will it take Joe to catch up to Mary? All right, here's our table again. Rate, time, distance, Mary and Joe. Okay, we know that Mary is traveling 3 miles per hour and Joe at 5 miles per hour. Their times, however, are different because Mary leaves beforehand. So we'll let t equal the time for Mary. Or actually, you know what? Let's change that. I'm going to let t equal the time for Joe. I think that might be easier. So we'll put t there for Joe's time. Now, if Joe has been jogging for t hours, Mary left 30 minutes before him, so her time is Joe's time plus an extra half an hour. She's been jogging an extra half an hour because she left before him. Okay, once again we're going to multiply across to get our distance. This is 3 times t plus a half, and this is 5t. Now, just like the last problem, we're going to set those distances to equal to each other. If Mary leaves and starts walking, and then Joe leaves later and then tries to catch up, the point at which he catches up makes the distances equal. So distances in this problem are equal. I'm going to set this equal to this. 3 times t plus 1/2 equals 5t. And that's what we're going to solve. 3t plus 3/2 equals 5t. Subtract 3t from both sides. 3/2 equals 2t. And then multiply both sides by 1/2 here. Times 1/2 times 1/2. Like that. And we end up with t equals 3/4. And so this right here is our 3/4. And that's the answer to the problem. Joe takes 3/4 of an hour to catch up. There's our problem solved. Okay, all of those, I believe there's 4 examples. Those 4 rate, time, distance examples are similar to the ones that you would see in your book, in your examples. So when you do a rate, time, distance problem in your homework, refer back to one of those problems. That one of them should be very, very similar to the problem that you have to do. One more application here, which is not a rate, time, distance problem, but we do need to mention it, and that it has to do with angles. The sum of the 3 angles in a triangle is 180 degrees from geometry. The 3 angles in a triangle, add them up, always add up to 180. We can use this fact to solve some word problems. On this one, we have one angle in a triangle is 15 degrees larger than a second angle. So what I'm going to do, I'm going to let x equal the measure of the second angle. So the first angle then says is 15 degrees larger than the second. That would make this one x plus 15. 15 more than the second one. The third angle, it says, third angle, is 25 degrees larger than twice the second. So that would be 25 plus 2x. I have now expressions for all 3 of my angles. Now I can write down my equation. The first, oops, that's not the first angle. Here's the first angle is x plus 15, plus the second angle x, plus the third angle 2x plus 25. All 3 of those angles should add up to 180 degrees. And so that's the equation I'm going to solve. This fact right here has been used there. Let's see here. We don't really need the parentheses. I'm going to get rid of them. Combine your like terms. I got x plus 2x. That's 4x plus 15 and 25 is 40. Subtract 40 from both sides. And I end up with 4x equals 140. Excuse me. Divide both sides by 4. Like that. And 140 divided by 4 is 35. Excuse me. 35. Now it says, that's not our answer. It says find the measure of each angle. So if I go back up, here, x is 35. That is the measure of the second angle. 35 plus 15 here is 50. That's the measure of the first angle. And the third angle is twice 35 plus 25, which is 95. And so my answer here is the angles. Let me fix that. The angles measure 50 degrees is the first angle, 35 degrees is the second angle, and 95 degrees is the third angle. And a quick check, if you add all 3 of those angles up, they should add up to 180. If they didn't, then we would have done something wrong. We'd have to go back and fix it. All right, that's the end of the lesson for our applications of linear equations.